do. This is a project which I started thinking on a long time ago when I was still in undergrad. And I return to it from time to time. It's a fun project to think about. And so let's start. So for today, we'll fix a finite, once and for all, we'll fix a finite field fq. So q is a power of some prime number p. And we will be considering sequences of geometrically connected smooth proper curves over Q. And we will be assuming that the genus in the sequence is growing to infinity. Yeah. So for any such curve over Q, we can consider its Picard variety, pic 0. It's an abelian variety, and its group of FQ points, it classifies, so it is the group of line bundles of degree 0 on X. So pic 0 is a variety over FQ itself, and this group of FQ points is a finite group. We can define the class number hx of X as the order of this group. And then a natural question is, given such a sequence with growing genus, how fast does hx grow compared to the genus? So as I said before, pic 0 itself is a variety over FQ, and there is a well-known method of computing a number of FQ points of varieties over FQ. Namely, there is a Grothendieck-Lefschetz fixed point formula which expresses FQ points as so yeah, given a variety y over FQ, its set of FQ points is the same as the fixed points of the Frobenius. This is an endomorphism which every variety over FQ has. And then one can prove that there is a Lefschetz type fixed point formula where instead of considering singular cohomology of the variety, we can consider its total cohomology. So here, if we are interested in the number of FQ points of Y, we need to take the signed sum of traces of the action of Frobenius induced on the étale cohomology of Y. So yeah, if you don't know what étale cohomology is, it does not really matter here. It's just some sketch of where the formula comes from. But anyways, so if we start with a curve X and then we consider its Picard variety, then we have a nice formula for its étale cohomology groups. Namely, they are just given by the exterior algebra on the first étale cohomology of X. And then using the fact that the trace of an operator acting on the exterior algebra, like wedge polynomials on some space V is the same as the determinant of F acting on V, we can show that Hx in fact satisfies the following inequalities. Oh yes, and here we use the Riemann's conjecture part of Riemann's hypothesis part of the Weil conjectures. So eigenvalues of fx star acting on h1 x have absolute value square root of q.
Jim, sorry, probably determinant of 1 minus f, right? In the formula above.
Oh yes, yes. Sorry. Yes, this is a mistake. I'm sorry. Yes, and then yeah. So from this you get this sort of bounds on the hx. So here, yes, yeah. So it's not hard to establish them, yeah. So here to gx is just the dimension of first total cohomology.
There was a question from Sudhir. Shouldn't be the sum and the trace formula go up to twice the dimension of y, not to the dimension of y?
Oh, that's true. Yes, sorry, another typo.
Okay, thank you.
Yes, yes. Yeah, I'm sorry. Yeah, so total cohomology behave similarly to how they do for complex varieties, particularly for a variety of dimension d, it will go from 0 to 2d. Yes, all right. So then, in particular, if we take logarithms of hx and we divide by g, then we get that the corresponding value, the corresponding quotient, is squeezed between two constants, depending on the q. Right, so this is given by twice logarithm, q-based logarithm of square root of q plus 1 and square root of q minus 1 correspondingly. So as q grows, these two numbers tend to 1, but still it's some non-trivial interval. And so in particular, having a sequence x, a natural question is, so yeah, we get corresponding sequence, the sequence of values of the corresponding function, the corresponding quotient. And the natural question is, when does this sequence converge? And the answer to this question was given by Tsfasman-Vlăduţ. And the key notion here is the notion of asymptotically exact sequence. So what it is? For curve x, let Bn of x be the set of points of degree n. So these are points of the underlying space of x, which are isomorphic to spectrum of fq to the power n. And then yeah, a sequence x of curves xi with growing genus is called asymptotically exact if for any n the following limit. So here I'm taking the size of the set Bnxi and divided by the genus of xi. So if all these limits exist, the sequence is called asymptotically exact. And the numbers, well, maybe this is not very conventional, but I will call them Tsfasman-Vlăduţ invariants of x. Okay, so yeah, this concept can, so yeah, the idea is that if a sequence is asymptotically exact, then the limit of this quotient exists as well. And this can sound a little bit weird. So we wanted to establish the convergence of one sequence, but instead we demanded the convergence of infinitely many other sequences. But the point is that for these sort of quotients, the convergence is much easier to check, as we will see. Okay, so if x is asymptotically exact, then one can write an explicit formula for the limit. So first of all, the limit the limit exists, and we can write an explicit formula for it using this invariance, Tsfasman-Vlăduţ invariance. So in the sum, they appear right here. And I want also to point out that before we have shown that this limit is greater or equal than the 2 twice logarithm q of square root of q minus 1.
Excuse me, there's another question. Could you maybe go back one slide?
Yes. Sorry for all the typos.
Yeah, the question was to explain what does spec f to the power fq of n? I mean.
Oh, so we have so fq to the power n is an extension. Yeah, so I don't know. I mean, so let's say x was
What do you mean
a1.
by this?
Just a scheme corresponding to fq to the power n. So maybe I will just give an example to get a feeling what's going on. So if x is a1 over fq, this is not proper, but still. So what I mean by this b and x, so points of x correspond to reducible polynomials in one variable inside fq of x up to scalar multiplication. And here I'm taking only ones which are of degree n.
Okay, then.
Yeah, I don't know if this helps, but
Right.
So I mean,
does it answer your question?
So fq is not algebraically closed. So points of the curve will be extensions of the ground field. And all extensions of fq are given by fq to the power n. And all closed points of x, they separate into the union of points under the order. And we are taking the order of the corresponding subset.
Okay.
Yes, so returning to this formula, before using Weyl conjectures, we have established a bound from below, which was given by this number, which is less than 1. But here you can see that asymptotically, if limit exists, it's always greater or equal than 1, because all numbers beta n are greater or equal than 0, and so do these logarithms. So this is already pretty surprising. Okay. Then, yeah, I mean, a natural question is whether we can apply this theorem to anything. So if there are any sequences for which we can tell right away that they are asymptotically exact. And in fact, there are. So if we take any tower of curves, which means I'm just taking a sequence of curves, and here I'm assuming that maps are dominant. Maps. And we also need to assume that the genus is growing, then this sequence is asymptotically exact. And this is not hard to show using the Riemann-Hurwitz formula. So then you just can show that these sequences for which we want to compute the limits, which give us beta n's, they are monotonically decreasing. And since they are greater than 0, you get that they have some limits. And in general, if you have an asymptotically exact sequence, you can always find an asymptotically exact subsequence. So in a way, this is the best you can hope. This formula is the best you can hope for. Okay, so I also wanted to say a couple of words about what these Tsfasman-Vlăduţ constants can be. A general result about them is the Drinfeld-Vlăduţ bound. So here it says that if we put some normalization factors, which are given by n quotient by q to the power n over 2 minus 1, then the sum of all of these beta n's should be less or equal than 1. And in particular, from this, it follows that each of them is less or equal than the inverse to the corresponding normalization factor. So this weird number. Another natural question is, given, for example, a tower of curves, if one can compute explicitly this constant. And this appears to be a very hard question. I'm definitely not a specialist in the area, but the impression I had that basically the only way to compute them is to show that one of these numbers, beta n's, is exactly given by its maximal possible value. And then using this theorem of Drinfeld and Vlăduţ, you can, it follows that all others are just 0. And well, maybe there are some other computations, but I'm not aware of them. I guess specialists can correct me, and maybe this is a good place to do that. Yeah, okay. So a particular example of such sequence for which you can compute its Tsfasman-Vlăduţ invariance is given by Garcia's 16-nodes tower. But for this, you need to assume that for this construction to work, you need to assume that Q is a square. Okay, then this tower, of course, is given by the following procedure. You start with x0, which is equal to p1, and then you do a sequence of Artin-Schreier extensions of the following form. So you add a new variable each time, which satisfies this sort of equation with respect to the previous one. And in this case, beta n is equal to q to the power n over 2 minus 1 divided by n. And from this, and the Drinfeld-Lattice bound, it also follows that beta I of it is equal to 0 for all I not equal to n. Okay. I think there are also some examples when Q is not a square, but where you can prove that some of the beta n's is greater than 0, but you can't compute them explicitly still. So this was a review of the classical story behind this computation of class numbers. And now I want to pass to non-commutative, or rather non-abelian versions of these formulas. So now we will fix also a split reductive group G over Q. And yeah, I will also at some point consider Q points of G. So by this, I will mean that G is given by its Chevalley model over Z, and we can consider its points over any base. Okay. So we will consider the stack band Gx of G bundles on X, and also a nice substack of it, a band G0, Gx, which is the substack of G bundles with generalized determinant 0. So what do I mean by this? By this, I mean that given any character psi from G to Gm, I want the corresponding line bundle. So given a E G bundle, I can make a line bundle xi from it. And I want it to have degree 0. Has degree 0 for any xi. Yeah, and here I'm considering only those xi which have infinite order, so which are surjective. So in particular, for example, if GLN, if G is equal to GLN, then I'm just considering vector bundles of rank n whose determinant is equal to 0. Yeah. If you are not very comfortable with the notion of stack and other things, we will be only interested in the sets of FQ points. So it won't really matter.
Not the determinant is 0, but it's just its degree is 0, yes?
Sorry? I just... you have your microphone turned off.
Sorry, you require that just the degree of the determinant vanishes, not the determinant itself, right?
Oh yes, degree 0, sorry.
Okay.
This was slip of the tongue, yeah.
So can you remind this band knot Gx is like something more of finite type than the whole band Gx, right?
Well, it's still not a
finite type condition.
Still not a finite type. So geometrically, it's a union of connected components.
Finite
band
right?
Gx. Yes, but yes, but it's still not a finite type. But the point is that for it, the G mass, which is defined below, so this sum. So here I'm summing. Here comes the definition of G mass of X. This is a sum over all G bundles over X. but of some normalized factors. So here we need to consider the weight. So each point has its own weight, which is given by the order of automorphisms of the corresponding bundle. Yes, and the point, so why we consider bun 0 instead of bun G, if we consider bun G, this sum is not convergent. So we'll just have infinite copies roughly of the same sum. But for bun G0, this is well defined. So it corresponds to some compact set in the Adels.
Yeah, that's what I wanted to ask. So it corresponds to the volume probably, yes, of the quotient of Adels.
Yeah, roughly.
Principal Adels, but you take only the Adels which are the kernel of all characters, yes.
Yeah, yeah. So if you multiply this by Tamagawa number, this will be exactly the volume. But,
okay, yeah, sorry. Yeah,
but yeah, Tamagawa number is finite, and in fact, it's, yeah. Assuming some strong results, you can, oh, sorry. My iPad is misbehaving. Okay, so let's consider a simple example. So returning to the previous case, when G was equal to GM, the stack bun 0 G M X will be just equal to peak 0 of X times B GM. So in particular, its points are just points of the Picard variety, but each point now has a small stabilizer given by the FQ points of GM. And when we do this sort of summation, what we get is just, again, the class number, but now divided by Q minus 1. And, in particular, if we want to establish an asymptotic formula for this, we see that this Q minus 1 factor does not really change anything. So yeah, we'll look at this example later in more detail. Yeah, and this motivates the question if after we fix some reductive group G, the analogous limit of the logarithm Q logarithm of the G mass of X divided by the genus still exists. First, and second, if it's still expressed through this Tsfasman-Vlăduţ constants. So, yeah, just as an example of how this could work, let's consider the case of the torus, split torus, Gm to the power n. In this case, Picard variety is this case band Gm to the power n is just given by the nth power of band Gm, and what we get is a summation over the nth product of peak 0 with itself of the FQ points of of this term. And this is equal to hx divided by q minus 1 to the power n. And then if we try to compute this asymptotics, so here what I will get is a logarithm log q of hx to the power n plus log q minus log q of q minus 1 to the power n, and this is just some constant. So when genus is growing, this will die and will not affect the answer. And so we get that this mass is expressed through hx, and in particular, we just the answer is given by what we had before times n. Okay, but of course, it's more interesting to consider some non-commutative situations, say G equal to GLN or SO or SP, or even some very complicated groups like E8. Okay. So before giving you the result, I need to introduce some new players in this story. So first of all, there is a function which is called L function of X. It is given as an infinite product over all points, close points of X, where we, each term is given by the following function, which is a rational, very simple rational function of in q to the power minus s. So here degree of x is what we faced before. So x is isomorphic to spec fq to the power n, and then degree of x is equal to n in this case. Then by while conjectures, one part of them proved by Grothendieck, this function, this infinite product, in fact, is itself a rational function in q minus s. And so its numerator is given by the determinant of 1 minus, so normalized action of the Frobenius on first attack of homology of x. And its denominator is given by analogous terms for h0 and h2, but I have written them down explicitly. So here, these are given by 1 minus q to the power minus s, and analogous term with q there. Yes. So it's you can show it's not very hard that this function is well defined. Yeah, so this I should have said it right away, that it's well defined if s is greater than 1, meaning that this power series, this infinite product, in fact, converges. But also, so at s equal to 1, this function has a simple pole, which you can see also from this description. And we can also define the residual term of this function, which is called the quasi-residue. And it's defined as follows. So I'm just erasing this term from the function, and looking at the limit of everything else when s goes to 1. And it's called quasi because it's not exactly the residue. There is some logarithm correction, log q correction. Okay, and then in fact, just putting the value s equal to 1 into this formula, one can explicitly compute. So using things we considered before, that this quasi-residue is just given by this formula. So it's q to some power, depending on the genus, times the gm mass of x. Oh, yes, and in particular, so from this formula, it follows that one can interpret Tsfasman-Vlăduţ formula as an asymptotic for log q rho x divided by the genus of x. Because in fact it expresses this in this way, and these are equivalent questions. Okay. Oh yes, and I also want to say that this is a particular case of Ziegel's mass formula for G equal to Gm. Now we'll formulate it in general. So for this, we will need to consider the algebra of G-invariant polynomials on the Lie algebra. So here, here I'm not very accurate. So here everything needs to be considered of the rational numbers. So I base change my split reductive group G to Q. I'm assuming it's defined over Z. Yeah, so I'm considering its Lie algebra, and I'm also keeping track of its centrum. So there is a central subalgebra in G. And then the algebra of G-invariant polynomials on G splits as tensor product of polynomials whose variables lie in the center, and also another polynomial algebra whose generators are homogeneous and all of whose degrees are greater or equal than 2. And these degrees are called the fundamental degrees of G. So in the case of GLN, these guys are given by coefficients of characteristic polynomials. So the Lie algebra of GLN is just given by matrices, n times n matrices, and these are the these are the coefficients of the characteristic polynomial. Oh yes, and maybe I should have said that here I'm considering the joint action of G on G. Okay, and then there is this nice formula. I guess it's not exactly due to Ziegler. So Ziegler established it in number field case, but it's very much analogous to that. So it's a formula for the G mass, and it's expressed as a product of several terms. So first of all, there is some q to the power G factor, but it's multiplied by the dimension of G. Then there is something which is called the Tamagawa number. I won't get into details of what it is, but it's a volume of some fundamental domain on an action of G of K on the quotient of the adels of K by the regular adels. And then there are factors which are related to this decomposition of the polynomial algebra. Namely, if we, namely there is a rho x factor which comes with multiplicity the dimension of the centrum, and then for each invariant polynomial of degree d, we have an L function factor. And yeah, here this is a finite product. Okay, so in the example of GLN, the dimension of G is equal to n squared. The dimension of the centrum of is 1. Tamagawa number is equal to 1. I think this was first computed by Harder in his paper with Harder and Narasimhan. Also, as I said, these invariant polynomials are given by coefficients of characteristic polynomials, and their degree are just integers, starting from 2 and ending with n. And yeah, so here, in fact, you can think of this rho x as a substitute of L of x1, which does not exist, but this is what remains of it. Yes, and then using this formula, you can prove a generalization of Tsfasman-Vlăduţ formula to this non-abelian setting. So let X be an asymptotically exact sequence, and then the asymptotic for this quotient is given by the formula on the right. And here, so recalling how the formula looked for Hx, so in the GM case, this dimension of G was equal to 1. And the corresponding factor here was given by Q divided by Q minus 1. So this way we see that this formula really interpolates between all the reductive groups G and specializes to what we had before for G equals to GM. Okay, so the proof actually is not hard, assuming some conjectures, not conjectures, but so if you use some strong results about Tamagawa numbers, probably you can use something much, something not that strong. Like you don't need an actual computation of Tamagawa number to show that they don't give any impact to this formula. But since this result exists, you can use them. And so by in particular, I mean the famous Weil's conjecture on Tamagawa number, which says that the Tamagawa number of the simply connected group is equal to 1. And from this, you can show that for any group, this Tamagawa number does not really affect the logarithm. Oh yes, maybe I should say that this formula is just obtained by applying logarithm to this Ziegel-Mass formula. So then the first factor exactly gives you dimension of G, and the other terms correspond to this sum. And yeah, so in the semi-simple case, in particular, how does this term with the group order of the fq to the power n points of G appears? So for each point, for each closed point of X, the product of the corresponding local factors in this L functions component of the mass formula is given exactly by the quotient which appears in the logarithm. It's not hard to show. I think it's known as Burnside formula. Yes. And in general, you also need to combine this with the formula for rho of X. So if your group has centrum, then using the work done already by Tsfasman-Vlăduţ, it's not hard. So in fact, for semi-simple groups, this formula is much easier than the original formula of Tsfasman-Vlăduţ. I want to point this out, even though the geometry behind is maybe much more complicated. Okay, but still, so this result is a little bit weird because this mass. So the problem is that if G is non-commutative, say G is equal to SL2 or something like this, already in this simple case, the number of G bundles, even if we assume that the generalized degree is equal to 0, it's still infinite. So what we were computing is just some weird value which was associated to X and G. But maybe instead we would like to give an asymptotics of some actual number of some geometric objects of X on X, as it was before for Tsfasman-Vlăduţ formula. So there we were computing class number, which was exactly the number of line bundles. So here the hope could be that we could compute, say, the number of semi-stable bundles on G. Or not on G, on X. G semi-stable bundles on X. Yes. So this is what we are heading to. But first, at least we could try to replace the mass by the semi-stable mass. So in this infinite sum, we could take only a finite subsum given by semi-stable bundles. And yeah, so I won't remind the definition of semi-stable bundle because it's too involved. But you should think of this. So we should think of this stack bun 0 as S, inside bun 0 as some nice finite type substack, very natural in a way, some sort of indecomposable or roughly almost indecomposable objects inside this bun G, some building blocks inside it. Okay, and yeah, so the initial question is if the asymptotic formula still works if we replace mgx with mgx semi-stable. So here I just took the same sum, but over only the semi-stable bundles. And the answer to this question is yes. Maybe this can be shown in more easy way, but the proof that I know should use certain complicated formulas. So the idea is that you can express the semi-stable mass for a given G through masses, L masses for L inside G being Levy subgroups. And yeah, of course, I'm fixing some maximal torus G inside T inside G, and I'm considering only those Levy subgroups which contain T.
Sorry, do you assume T is split? That's not necessary here.
Oh yeah, so here for simplicity I assume that G was split.
But the theorem holds true in general.
I have not thought about semi-stable case. I'm not sure how Narasman harder Narasman filtration works for non-split guys.
Yeah, okay.
But if it works, it's fine. Yeah, so this is just some combinatorial formula which applies given you have some assumptions. So so this formula, it's purely combinatorial. It does not have, I don't think it has a geometric interpretation, but the one formula, you can express mgx in the other direction. So you can express mgx through semi-stable masses for else with respect to Levy subgroups for all else. But you also need to introduce some degrees here.
Excuse me, and they'll correspond to unstable points.
Yeah, so here, yes. So if all terms except L equal to G correspond to unstable.
Okay.
So
Yeah,
this summons corresponds to types of Harder-Nariman filtration associated with graded pieces. And then the thing is that you can invert this formula using some combinatorics which Langlands established for establishing Langlands correspondence. And this was, so there is a paper by Lomon and Rappaport. Oh, sorry. Where they use this formula to compute the Betti numbers of moduli space of semi-stable bundles in 360 G semi-stable bundles. And you can essentially use the same formula, but you need to put, you need to check some other things. Like when you compute number of points, you get exactly a formula of the same type as they have. And then, yeah, so you can, this is sort of Möbius inversion formula. So you can express by induction these semi-stable guys through mgx back. As an example of how this formula looks, in the case of JLN, so it's the sum we get is a finite sum. It's important that this sum is finite, and so yeah, maybe another comment that in this sum given by Harder-Nariman types, this sum is infinite, and it's very hard to use it for any computation. But the inverse formula will be finite, and this is very nice. Yeah, so the summons will be encoded by Levy subgroups of X, and so here each term, so here we have ML. Here the corresponding Levy subgroup is just given by the block diagonal matrix given by JLN1, JLN2, and so on. And it comes with some normalization term here. And then you can check that in this sum MGLN X, so the term for the partition n equal to n, dominates every other. And in particular, the limit of it is the same as the limit of the whole sum. Yes. And yeah, so maybe this is not clear. The number of semi-stable bundles is less than the number of all bundles. And here, this function psi n, it actually contains signs. So this is in a way signed difference of positive values. So by this I mean that if you, for example, take partitions consisting of two terms, then there is a single term here, and we see that it's negative. So what we get here is actually a signed sum. So it's a yeah, sum of plus minus of terms corresponding to the Levy subgroups. Okay, yeah, I'm sorry, this might seem a little confusing, but so after you have the formula, in fact, it's very easy to show that the limit does not change. So this is more like an observation than an actual complicated result. Okay, but still, if we want to count the number of semi-stable bundles, we have not yet established this, because let's return to this slide. Here we had a sum. Here we have these normalization factors given by the automorphism, orders of the automorphism groups of E. So this poses a question if we can bound in a way this automorphism groups. So namely, given a curve X and a G semi-stable bundle on it, what we can say about its the order of its automorphism group. Okay, and so here comes the key result, which I find the most complicated. Here, so it says the following. So X, as before, is a smooth geometrically connected proper curve over FQ. And we assume that there is an FQ to the power n point of X. So there is a map X from spec FQ to the power n to X. And then I also need to add some further assumptions on G, or rather the prime P. So here again, P is a characteristic of FQ. So Q is equal to P to the power K. And we need P to be greater or equal than the Coxeter number of G. So for G equal to GLN, this is equal P, H of G is equal to N. And then for any G semi-stable G bundle X, we have the following bound. So the automorphism, oh sorry, maybe it's a bad idea to call it X, let's call it E. Then the automorphism group of E is, oh yes, sorry, this is also should be less or equal. The automorphism order of the automorphism group of E is less or equal than the order of G, FQ to the power n points of G. And in fact, so how does the proof go? What I show is that given X, we can consider pullback X star of E. This is just a vector space on, well, this is a G bundle on the spectrum of Q to the power n. By length lemma, it is trivial. And what we show is that the pullback map X star from the automorphisms of E to the automorphisms of EX is an injection. And this can be described as just FQ to the power FQ to the power n points of G. Okay. Yes, and so under some further very mild restrictions on this sequence, this gives the desired bound on the automorphisms group of semi-stable bundles. So the difference between the weighted sum, namely like the sticky count of points on the semi-stable locus, will differ from the actual count by some constant, depending only on Q and G. Yes. And so if we denote by SS of X the set of semi-stable G bundles on X, then we get the following result. So if P is greater or equal than the Coxeter number of X, and X, curvy X is a asymptotically exact sequence, satisfying some further conditions. So here this is not, so you can actually ask for something less strong, but let's assume that the following holds. So there exists N such that each of these Xi's have an FQ to the power n point. Okay, so for example, if X was given by a tower of curves, this would be automated. Holds if curly X is a tower of curves. And yeah, then in this non-abelian version of Tsfasman-Vlăduţ formula, we can replace the GMS by the size of SS of xi. The number of semi-stable bundles, G semi-stable bundles on xi. Yes. And then the natural question is if these assumptions are really needed. As I'm pretty sure that these are just artifacts of the proof. That maybe a person who understands the situation much better, the geometry or the analytic part of it, will have no problems to establish such result.
Sorry, I lost a little bit the logic. So in the assumption, you assume that there is n large enough such that, and then you take the sum overall n starting from n 1. So,
oh, sorry. This is, yes, I'm sorry. This is bad coincidence. So the formula usually uses n as an index, and here I used it in the other way. So here the sum is over.
Yeah, but then
yeah,
I don't see. So well,
yeah. So the thing is that yes, if this condition doesn't hold, the sequence could still be asymptotically exact. So all beta n's would be 0 in this case. But maybe the formula won't hold. So I mean, if there is an asymptotically exact sequence which does not satisfy the condition in the lemma, all beta n's are asymptotically all 0 automatically. But the problem is I can't.
Yeah, I'm just a little bit confused because your denominator g of f q to the I.
Yes.
Does it come from the previous result? This.
Yes.
Oh no. But no. I mean, the upper bound on the number of automorphisms.
No, it does not. So.
Okay. Sorry. Okay. Yeah,
yeah. So this guy comes just as term from the old version.
I see.
Yeah. Sorry. This
I see.
does not have to do. So the automorphisms of these bundles do not appear. In fact.
Oh, thanks. Yeah, sorry.
So this was, sorry, this was confusing. So I used only the fact that all of them are bounded. So if we were over an algebraically closed field, then it would be easy to say that. So if I have a semi-stable bundle, then if an automorphism is trivial at a single point, it's also trivial globally. But here the problem is that you want to pick a point, but maybe this point is of order which is big compared to Q. And this is sort of issue we are fighting with imposing this condition. And in fact, you can allow this n not be constant, but grow with I, just not very fast. But unfortunately, while conjectures don't allow you to say that there is always such a point that blah, blah, that this bound will be sufficient. So you need to do something more accurate. And I did not come up with it. Yeah. So this is basically it. Maybe I just want to add a few comments. So in fact, everything works except at least the part before this semi-stable counts. If we take any pullback of any reductive group from FQ, it does not need to be split. And in the case when G is a torus, this was Kunyavsky-Tsfasman conjecture that such a formula works. And this was a project which Alexey suggested to me when I was in my second year, I think. And then I also competed in a Möbius competition and got a second prize for proving it. And all what I was telling you today was telling you about today were just some thoughts I have had afterwards. Why not to try to generalize this to other groups? The geometry is much more involved. Geometry of the classifying, the stack of G bundles is much more involved. So yeah, in particular, I found this as a very good subject to talk to on such a occasion. Yeah. All right. Yeah. Thank you.
Okay. Thank you. And let's thank the speaker. And Yes, basically the principle of this conference was that we share mathematics that would have been interesting to Alexey. That imagine that Alexey is present in the audience, and well, I'm pretty sure that this talk would have been interesting to him. Are there any questions? If you have a question, just please turn on your microphone and camera.
Okay,
All right.
can I ask a question? Okay.
Okay,
Yes.
Is it known something similar formulas for algebraic surfaces? For example,
I think
Hilbert schemes or what, or for algebraic surface or something, torsion-free shapes or.
Yeah, I'm not sure. I mean, it's a very natural question to ask. I think Tsfasman was trying to establish something with Kuniavsky in the paper about elliptic surfaces, but computation appeared to be very hard. So I'm not sure. Yeah, I think I'm not the right person to address this question too. Maybe somebody in the audience will.
Maybe Misha can comment on that.
I can answer, I can try to answer. For surfaces and high dimensional varieties, the only thing we know concerns the elliptic case. And in the elliptic case, there are two different situations. So you consider an elliptic curve over the curve of growing genus, or you do not grow the genus of the base curve, but you grow the discriminant of the elliptic curve. These are two different situations. So the first situation is the still unproved conjecture of Kuniavsky and myself, which was done in the easiest case when it's just a direct product. Even then, we don't know the answer, we can only conjecture it. So Alexey Zykin tried to generalize it to any elliptic surface. So his conjectural formulae are much more difficult and unproved as well. And the situation when the discriminant grows and the base curve is fixed is a joint paper by Dmitry and Pacheco, where of course the pre-assumed divergence Simonoton conjecture, and there is some relation with the height of that elliptic curve, and again there are some inequalities, but we do not know the answer, so that's it.
Also, I understood that probably, I figured that probably I misunderstood the question. So what's the question about moduli space of sheaves on surfaces? Okay, probably doesn't matter. But I think if you try to study band G for on any moduli space of sheaves on surfaces, then at least similar methods like Ziegel mask formula, they fail because you can't use these adelic techniques since the corresponding sets are no more locally compact. So you can't formulate anything in terms of some measures. Yeah, but you can use some more geometric approaches by work people have probably done.
Okay.
Okay, I have a different question. So, is something known in the generalization when you take a non-constant group G over X? The group was defined over Q from the beginning, right?
Yes, yes. So again, I have not thought at all about what you should substitute the semi-stable condition with, and if the corresponding stacks will be finite type. Provided this is true, I think everything should work. Again, so the thing is, you want to reduce somehow to simply connected case. And I think the work of Gatsgori and Luri about the Tagawa numbers, they prove it for any family on G.
Yes.
So I don't think this should be a problem, but I did not think about any details.
Okay, thank you.
Okay.
Have you written it down or not yet?
Not yet. I'm kind of, So I'm working on other projects, and I did not feel motivated enough to write this down. This was just like a fun side project, which I'm dragging on for several years. But yeah, I mean, if you find this interesting, I could try to write it.
And is the case of theories published or not yet as well?
No, I don't think it's published. I mean, it's available on the website of Möbius competition, but I don't think it can be counted. It also wasn't revised properly, I think.
Maybe it's worth doing it. Both, I mean.
Yeah, okay. Maybe spare time this summer. I'll try.